An evil thing with parallel programming is the data races that may occur and the locks that are needed to prevent programs from having data races. Data races is the most vicious thing that you will ever see in parallel computing. So we're talking about race conditions. A race condition exists if several threads may access a shared resource, typically memory location, and at least one of them modifies it. This means that this modification might be viewed in different ways by different threads, and also, depending on the interleaving of the threads, there might be indeterminism, so the program will not have the same result every time it executes. So this is a consequence of, typically a consequence of relaxed memory models that you will hear more about when we talk about parallel computer architecture. Just as an example, this also exists in the real life. Let's assume that you are, like me, shopping at some computers, some stores, for instance, Shell Company. I look up the web and I see if there is a particular item that's in stock, and let's say that there is one item in stock left. And then two persons check this at the same time. So we both look at the stock, we see that there is one item left. And then we go to the store, and depending on the one that comes first, the other will go home unhappy. And this is a race. It's a race to the store to find the item that you want to buy. So mutual exclusion is the model to resolve data races. That's sort of the standard model, which is not always the best for high performance, but it's a working model. So a critical section is a part of the code where there is only one thread may execute at any given time. So the threads have a mutual exclusion access to the critical section. Again, going to this stock checking example, so when you check the stock online, you request the store to hold it for you. So you request the store to have mutual exclusive access to this particular check. So the checking and reservation has to be done atomically, so that only one person can reserve it at any given time. And there is no need to race. You can take all the time you like to go to the store and get it. But obviously, this kind of locks limit parallelism, because if you have to lock access to a data item and you're not really using it, then no other thread can use it also. So use locks carefully. And locks can also lead to deadlocks, which is problematic. So let's see here how this looks in code here. So let's say that we have a price comparison algorithm. We are trying to find the best cost for something, and you do this in parallel. And my thread is looking at something, and then we have a shared variable, the best cost, which is the currently best cost, and all threads share this variable. So here we have a case where there might be cases. So we have one thread here that finds out that its my cost 0 is smaller than best cost. And then you have another thread that does this at the same time. And they both find out that their cost is smaller than the best cost. Depending on the interleaving of how the threads interleave the code, it could be that the best cost is either my cost, in this case my cost 75, or my cost 50, depending on which one performs the store here the first. So we have both an incorrect program, because it's possible that best cost is given the value of 75, but indeed the lowest cost is 50 here. And also it's indeterministic, because some executions you get the best cost of 50, and some executions you get a best cost of 75. So this is not a good good way to do it. With C++11, you can define critical sections by means of mutexes. So you define a mutex like this, and then before you check the cost and then update the cost, so the critical thing here is that you have to make sure that once you start checking, doing this comparison here, you cannot allow anyone else doing the update of best cost. So you lock this by locking the mutex and then unlocking the mutex. So this is a simple way of doing a protection and doing a protecting some code here. This is not exception safe. If there is a an exception that happens inside here, now it's not likely to do in this simple case, but you could have a memory exception, for instance, and then the lock would be locked for eternity before coming back here. There are ways to deal with that when you have exceptions in C++, and it's called a guard lock, but this is sort of out of the scope of this presentation here. So here we have a comparison and an update. There are other ways where you need locks, but possibly you wouldn't realize that. And that's when, for instance, you have a variable that you do just an update on, a++, for instance. A++ will load A to a register. You will do an add operation on this register, and then you would store this register to A here. So you have at least a sequence of 3 instructions to do this A++. And if you have 2 threads that does this simultaneously, you have every sort of chance of getting different kinds of interleavings of these instructions, and therefore there is a need to protect this variable with a lock or something else. With C++, 11, you have actually a way to declare, I think this is, I forgot, I don't know the syntax here, but I think this is basically how you do it. You have declare an atomic variable with the template int, is an atomic integer, then A. Then the compiler has to insert protection mechanisms to make updates to A atomic. It will not protect to this kind of situation when you have an if statement and then an update, but it will protect this kind of statement. It will also protect single I'm doing it with D, for instance, or QD, and let's say that QD is a I think this is what is called quad float. I'm forgetting now the name of it. So when you have a quad precision floating point number, then if you put this with atomic, updates will be done atomically. Otherwise, a quad precision floating point number, which is typically 16 bytes of size, then that will not be done atomically. It will be done with several bus cycles by the processor, and between 2 bus cycles, any other core can intervene and for stores to the same variable, and partial store may be a result of that. So locks for sequences like this, for making critical sections, atomics for variables that you update like this, or for stores that need to be atomically done.